To understand Bose-Einstein condensation, we first have to talk about the players involved, bosons. Unlike electrons, which are fermions and essentially ions that cannot occupy the same space, bosons are social particles with integer spin. Crucially, in quantum mechanics, bosons are indistinguishable. This means if you swap two of them, the physics of the system remains exactly the same. Because of this, they are not bound by the Pauli exclusion principle. They are allowed and actually prefer to crop into the exact same quantum state. At high temperatures, they act like normal billiard balls, but as we cool them down near absolute zero, they lose their individual identities. Suddenly, a massive fraction of the atoms collapse into the absolute lowest energy state simultaneously. This is what we call macroscopic occupation. It's not just a few atoms, it's a huge portion of the gas acting as a single giant superatom. This pile up in the ground state is the Bose-Einstein condensate. Now, let's look at the mathematical engine that drives this phenomenon. On the screen, you see the Bose-Einstein distribution function, which calculates the probability of particles occupying a specific energy state epsilon. There is one rule here that dictates the entire system, the constraint. The chemical potential mu must always be less than the ground state energy. Why is this necessary? Mathematically, if mu were greater than the energy, the exponent would be negative. The denominator would be negative, and we would end up with a negative probability, which is physically impossible. So the math demands that mu stays trapped below the ground floor. This constraint is actually what forced condensation to happen. As we lower the temperature T to zero, the chemical potential pushed upward to keep the particle count the constant. It eventually gets spin just infinitesimally below the ground state. When this happens, the denominator for the ground state vanish and the occupation number doesn't just grow, it diverges to infinity. Let's look at the simulation. We begin at a high temperature, represented by the red curve. As the system cools, the particles lose energy and the distribution narrows significantly. We can see from the curve that drops and turns to purple. Finally, as we approach absolute zero, we see a massive spike at the ground state. That infinite peak is the condensate forming. We can see from the blue spike that shoots up. This confirms that the BEC isn't just a theoretical curiosity, it is a mathematical inevitability for bosons at low temperature.
Let's look at the phase transition condition. As temperature decreases, the chemical potential, or mu, approaches zero from below. It indicates that the system is reaching the condensation threshold. The number of accessible states per particle decreases, and at some critical point, more particles are forced into single states. The excited states essentially reach their maximum capacity and cannot accommodate additional particles, even though they remain thermally accessible. Below the critical point, a large fraction of bosons occupy the lowest quantum state, making microscopic phenomena visible at microscopic scales. The maximum number of particles in excited states is given by this particular formula. Basically, critical temperature is the temperature where excited states can accommodate all n particles with mu equal to zero. It is also known as transition point, marking the temperature where bosons make a transition from a classical gas to a Bose-Einstein condensate, with atoms collapsing into ground state. Let's move on to the derivation of critical temperature. The probability that a particle has energy epsilon is given by the Bose-Einstein distribution. The total number of particles in the system is given by n, which is the integral from 0 to infinity g of epsilon times f of epsilons with respect to the epsilon. For free particles in a 3D box, the density of states is v over 4 pi squared times to m over h bar squared to the power of 3 over 2 times the square root of epsilon. The maximum number of particles that can be accommodated in excited states at the critical temperature occurs at mu equals to zero. We introduce a new variable x to be beta times epsilon to solve the equation. The remaining integral can be determined by applying Bose integral. So the result is the multiplication of gamma function times zeta function of 3 over 2. So the value of gamma of 3 over 2 is equal to the square root of pi over 2. So therefore, we can get this final equation. We know that the number density is equal to the number of particles over volume, and the value of zeta of 3 over 2 is equal to 2.612. So we can rewrite the final critical temperature as the final equation shown. From the derived equation of critical temperature, we can make a physical interpretation. We found that critical temperature is directly proportional to density to the power of 2 over 3. So the higher the density, the higher the critical temperature. Doubling the density will result in increasing critical temperature by a factor of 2 to the power of 2 over 3, or equals to 1.59. Denser systems are easier to condense into Bose-Einstein condensate. We also found that the critical temperature is inversely proportional to the mass. So the higher the mass, the higher the critical temperature. So doubling the mass will result in decreasing critical temperature by a factor of 1 over 2. Since electrons have lower mass than atoms, electrons would condense at relatively higher temperature. Let's see the connection between the Broglie length to the critical temperature. So the Broglie length is equal to h over the square root of 2 pi times m times k times t. So just rearrange the formula, we'll get the formula as shown. Substituting the last expression and the formula of number density, we'll get n lambda to the third power is equal to 2.612. We found that the Broglie length is approximately 1.4 D. At high temperature, the Broglie length is small, particles are distinguishable, and at low temperature, the Broglie length becomes comparable to distance d. Quantum wave functions overlap, no longer be treated as distinguishable particles. So when overlap is significant, condensation occurs. Here's an example of the calculation of critical temperature. So this example requires us to calculate the critical temperature of rubidium-87. So just by using the formula of the critical temperature, we can find the critical temperature of rubidium-87 atoms, which is about 170 nanokelvin. This table shows the critical temperature of several atoms. So since we have calculated the value of critical temperature of rubidium-7, which is about 170 nanokelvin, we can actually calculate another critical temperatures too by using the same formula. So from here, we can see that helium-4 has the highest critical temperature, which is 4.7 microkelvin.
Now I will discuss the condensate fraction of an ideal Bose gas below the critical temperature. When the temperature is lower than Tc, a large number of particles start to accumulate in the ground state, forming a Bose-Einstein condensate. The fraction of particles in the condensate is given by n1 over n equal to 1 minus T over Tc power of 3 over 2. This equation shows how the condensate fraction depends on temperature. For first example, T equal to 0.8 Tc, the condensate fraction is about 0.28. This means around 28% of particles are already in the ground state, while most are still in excited state. For another example, at T equal to 0.5 Tc, about 65% of the particles occupy the ground state. This indicates a strongly developed Bose-Einstein condensate. At very low temperatures, such as 0.2 Tc, more than 90% of particles are in the condensate. The system is now dominated by macroscopic quantum behavior. Next, for zero temperature limit, as the temperature approaches absolute zero, the condensate fraction approaches 1. All particles occupy the ground state, forming a pure Bose-Einstein condensate. This T power of 3 over 2 dependence is a signature of quantum statistics. At low temperatures, particles lose their classical individuality and behave as a single macroscopic quantum state. Next, for the concept of internal energy. Below the critical temperature, particles in the ground state have zero kinetic energy. Therefore, only particles in excited state contribute to the internal energy. For heat capacity formula, heat capacity at constant volume is defined as Cv equal to partial U over partial T. For T less than Tc, the heat capacity Cv proportional with T power of 3 over 2. At the critical temperature, Cv exhibits a sharp cast, which is the thermodynamic signature of Bose-Einstein condensation. In contrast, a classical ideal gas has constant heat capacity, Cv equal to 3/2 nkb. Let's make it more clearly by looking at the graph. Below Tc, the curve rises smoothly, and the most particles remain in the condensate. For T equal to Tc, which is the cups, we can see the dashed vertical line. The heat capacity is continuous, but its slope changes abruptly. Above Tc, heat capacity becomes nearly constant and approaches the classical value. For the entropy from heat capacity, the entropy of the system can be obtained from the thermodynamic relation. As the temperature approaches absolute zero, the entropy approaches zero. This behavior satisfies the third law of thermodynamics. At zero temperature, all particles occupy a single quantum ground state, so they are not accessible microstate. Classical theory fails at low temperatures, highlighting the necessity of quantum statistics. For this one, below the critical temperature, entropy decreases smoothly and goes to zero as the temperature approaches absolute zero, satisfying the third law of thermodynamics. At critical temperature, the entropy remains continuous but changes its behavior, signaling Bose-Einstein condensation.
Moving from theory to reality, it took 70 years, which is a 1995 breakthrough was the creation of the first Bose-Einstein condensate in the lab. This was achieved through a two-stage cooling process. First is laser cooling, uses precisely tuned laser beams to slow atoms down to a crawl. Then evaporative cooling is used. The hottest atoms are selectively removed and letting the remaining cloud reach temperature just a few billionths of degree above absolute zero. The experimental setup is a masterpiece of atomic physics. Atoms are trapped and cooled in an ultra-high vacuum chamber using a combination of laser beams and magnetic fields. This achievement was awarded the 2001 Nobel Prize in Physics. Its significance is profound. It gave us a pristine quantum control laboratory in a chip-sized device to stimulate complex quantum phenomena from superconductors to the early universe. Sometimes, quantum mechanics isn't just in equations, it is right in front of us. This is superfluidity, a quantum effect on a visible human scale. The classic example is helium-4. When cooled below 2.17 Kelvin, it undergoes a dramatic change and becomes a superfluid. This leads to bizarre behavior like the famous fountain effect, which is we can refer the image on the left side, where heat actually creates a jet of liquid that shoots upward defying gravity. The best way to understand is it's liquid that flows without any friction. Imagine a whirlpool that never stops spinning or a fluid that can climb straight up the walls of its container and escape. That's the bizarre, frictionless reality of a superfluid. It's stunning bridge from the quantum world to our own, showing us principles that also govern superconductors and even the insides of neutron stars. 4 key takeaways. First is condensates are the ultimate quantum ensemble. Second is superfluids flow without friction. Third, ultra-cold atoms are pristine quantum simulators. And last but not least, this state unified theory, experiment, and application. From lab to world, these aren't just curiosities, they are powering quantum computing and sensing high-temperature superconductivity research. Models are models of cosmology and neutron stars. Why it matters? This is more than physics, it's a new lens on nature, enabling technologies and understanding that will define our future.